All right, up to this point, we haven't been doing much math. We're just using rules and properties to try to go from one format to another. So we've done, for example, we've done exponential to logarithm, and we've done natural base to natural logs, and how to rewrite them from one to the next, going both ways. So these are the notes that we last did together in class. We talked a lot about inverses, and we talked about inverse operations. So addition to subtraction, division to multiplication, powers to roots. We're going to get back to this for this section because we're going to start solving. So with this, I kind of just want to get into it. When we when we see these things, say for example, I have like something really, really basic, like say I have 3 to the power of x is equal to 3 to the power of 2, and I want to know, what does x equal? So what is x? Now some people might see this and they will say, well, 3 squared is 9, so we have to start off with that. Actually, you don't. This is already set up for you so that you can solve it right away. When you have the same base, and you know that they're equal because they're telling you they're equal, then that implies that your exponents are equal to each other. So this is just x is equal to 2. Now, it's really obvious to see it when you have bases because you know the 3 and the x and then exponent 2 are just one term. But this is still true when you have exponents that are not just one term like this. So let's take, for example, and this is kind of starting into the new thing a little bit. Say, for example, we have 7 to the power of 3x plus 5 is equal to 7 to the power of 1 minus x. And I want to know, what does x equal? So again, here, my bases are the same. So that tells me that my exponents are also the same. So I can set 3x plus 5 equal to 1 minus x. Again, my bases were the same. Therefore, since this tells us where it's equal, my exponents also have to be the same. So going back to our notes from the other day, we're going to use inverse operations to solve for x. So add x to both sides. Remember, you want to combine the like terms. So you don't want to combine it with a 5 because those are not like terms. You get 4x plus 5 is equal to 1. You get x is equal to negative 1. Now that one was a little bit longer than the first example we did, but it wasn't necessarily difficult. It was just solving for x using our inverse operations that we learned a really, really long time ago. So I'm going to start one off, and then you're going to finish it for me. So let's look at something. This is so messy, sorry. Let's say we have something like 6 to the power of 2x minus 6 is equal to 36 3x minus 5. So showing the examples I've done before, this one looks a little bit different. We can look at this and say, oh, I don't know how to do it. Skip it, next, I'm done. And that's really, really easy to do, right? Just quit. But let's not. I noticed right away that the 6 and the 36, those are the two things that I want the same, but they're not. Here I had a 7 and a 7, I had a 3 and a 3. 6 and 36 are not equal to each other, but I can manipulate my 36 so that it does have a base of 6. Because I know, so little side note, I know that 6 squared is equal to 36. I know that. So why not rewrite my 36 into 6 squared? So I'm rewriting this part here while still bringing down the first exponent that it had. So again, I rewrote my 36 so that I could have the same base as my first part of this problem. So I manipulated to get the same base so that now I can make my exponents equal to each other. 2x minus 6 is equal to 2 times 3x minus 5. Remember that 2 came from 6 squared. So since it's an exponent, I just multiply these out and I get 6 minus 10. Oh, sorry, 6x minus 10. And again, use my inverse operations. I'm going to subtract 2x. And I'm going to add 10. So I get 4 is equal to 4x. X is equal to 1. Okay, so I want you to practice on your own. Here is a new problem I want you to do. So go ahead and pause it right here and solve that problem. When you're done, you could unpause and I will have the key for you. All right, and there is my key for this problem here. So you see I got the same base. I knew that 8 was something that I can change to a base of 2. And then I distributed that 3 into the initial exponent that I had. So that's where I got this 3x minus 3 here. I brought down my first exponent. And then I just set them equal to each other. If the bases are the same, the exponents are the same. Solved using inverse operations, and I got x is equal to 4. Now this is pretty neat because this same rule applies when you have things such as e and also logs. So 7x plus 3 is equal to log base of 38. So again, you can pause here and solve these on your own. For the first one, since the bases are the same, it just is one of these, 3x minus 1. So then I get negative x is equal to negative 1. So x is equal to a positive 1 here. I didn't show all of my steps for that because it's just inverse operations. I hope I didn't make a mistake though. And then the logs are the same. The bases, they're both 10. Remember that if it's not there, it means it's a 10. Therefore, the terms would be equal to each other too. So 7x plus 3 is equal to 38. Move the 3 to the other side. And solve for x. This would also be true for natural log. As long as you get them the same, so same bases or same logs or same natural logs, your exponent or your other term, you can set that equal to each other. All right, let's look at something a little bit more complicated. Okay, so with these that we did, we had terms on both sides. So here we had x's on both sides, but we had e's and e's, right? We had a base of 6 and a base of 6, or we had logs and logs on both sides of the equal sign. But what happens when one side has a log and the other one doesn't? And we still have to solve for the x. So we can't set things equal to each other because this has a log base 2 and this is just a number 3. Same thing here, the log is only on one side. So these two can't equal each other if there's only a log on one side. So we have to go back to our regular inverse operations to see how far we could get until we could actually solve this. So I'm going to stick to the same addition, subtraction, division, multiplication, and if needed, then I'll rewrite and see what I can do at that point. So again, these are still the same notes from 6.2. So looking at this first one, let me zoom in because you're going to do the second one. Sorry about that. Looking at this first one. Now, I have this 3 here, and I know a lot of things here. I know I could rewrite this and condense it so that that becomes a power. I know I could expand this until addition, but I really don't want to make things longer than they have to be because I want the x to be by itself. So I actually want to get rid of things. I want to get rid of eventually the log. I want to get rid of the 3. I want to get rid of the 4 because I want this x right here. I want this to be by itself. That's my goal. I'm trying to solve for x, right? So let's start off by using those inverse operations to try to isolate that x as much as possible. The only thing I can do at this point here, I mean, I can't divide by 4 because that's inside of the log. But the one thing I could do is divide by this 3 because it's in the front. So I'm going to divide both sides by 3. That would cancel that part out, but what I do on one side, I also have to do on the other side of the equal sign. So when I do that, I am left with log base 2 of 4 to the power of x, or 4x, sorry. And then 9 divided by 3 gives me 3. All right. So here, I can't really get any closer to the x because my log is there. I can't do anything with the 2 because that's just the base. I can't use inverse operations at this point because it's locked. It's locked inside of that log. I can't separate it unless, going back to this, instead of a log, I turn it into an exponential. When I do that, that log disappears and it's no longer locked into that log. I can move things a little bit more freely. So I'm going to draw my whale. Remember my little whale. And I get 2 to the power of 3 is equal to 4x. Now this works out nicely because now the variable is free for me to move around. That 4 I can eliminate more freely than when it's locked inside of a log. I can't do anything if it's as part of a log. So here, 2 to the power of 3 gives me 8. 4x divided by 4. X is equal to 2. So before I let you go to your own, which is this one over here, I want to walk through this again. You could pause it here if you're ready to start, but I'm going to review this. Because the x and the 4 were locked inside of a log, I couldn't get to it, but I could get rid of that 3. So I divided 3 on both sides, and that gave me this. Now to unlock it from inside of that log, so it's not stuck in there, I rewrote it into exponential form. So it was 2 to the power of 3 is equal to 4x. Remember my whale. 2 to the power of 3 gave me the 8. Now I just used inverse operations to solve for the x. So go ahead and pause here and solve this one on your own. Okay, so again, this part is part of my log. It's locked in there, so I can't get to it, but I can get rid of that 4. So I'm going to go ahead and divide both sides by the 4. When I do that, I get my log base 3 of 2x minus 1. 16 divided by 4 gives me 4. Okay, now there's nothing I can do here because it's all part of that log, but I can break it up from the log by rewriting it into exponential. So again, I'm going to do my whale. 3 to the power of 4, 2x minus 1. 3 to the power of 4 is 9 times 9, which is 81. Using inverse operations, you get x is equal to 40. Here's one more for fun. If you feel like you need just a little bit more practice, go ahead and pause here and solve this one. Okay, and you should have gotten x is equal to 6. And here's how I did it. Notice I'm not showing all of the little steps anymore. Okay, so before we get into one of the more newer ideas, like these are all new concepts, but these are like a more of a foreign idea, something we haven't really talked about. I want to go over what we've done so far. So we've been trying to find things that we can set equal to each other for the first part, right? So we had like 3 to the power of x and 3 to the power of 2. Since the bases were the same, we know that the exponents are also the same. Sometimes we needed to manipulate it a little bit, so change the base so that I could have the same and set those equal to each other. And then we also talked about what happens when you can't set both sides equal to each other, what we do in those cases. But something we didn't talk about yet, which we're going to do now, is what happens when you have things that are similar, but you can't get the bases to equal to each other. So what if this 36 couldn't be turned into a base of 6, or the 2 couldn't go with the 8, so the 8 couldn't be turned into something with a base of 2. What do we do in those cases? And that's what we're doing here. So looking at this 2 to the power of x, we can't turn the 7 into anything with a base of 2. They're just not powers of one another. So what do we do in these cases? I'm going to go back to the notes that we did with the exponent rules, because we talked about that these were also inverses of one another. So just like we use addition to get rid of subtraction or division to get rid of multiplication, we can use these as inverses of one another. So we can use an exponential to get rid of a log, or a natural log to get rid of a natural base. These go both ways. So let's use that to solve for this. Now, in the last video, we talked about that when you have a log that has the same base as it does term, that is always going to equal 1. This is always, always, always going to be true. Whether you have a 7, a 10, a 12, and 100, if your base is the same as your term, then your answer is always 1. So why do we need to know that? Why is this helpful in these cases? Well, you notice all of our exponents have that variable that we want to solve for. So using our rules that we did in the last video also, we know certain rules that can help us rewrite these things. So we're kind of applying everything we've learned so far into this to try to solve for it. So when I see these kind of expand it, but they don't get rid of the log itself. I want my exponent to be the thing that I'm solving for. So if I use this property, that'll bring it down so that eventually, if I know how to get rid of the log, I can get that x by itself. I want to detach it from the log. So I want this to come out in the front. But in order to do that, to use the log property, I need to turn this into a log. And I can use that to my advantage. So if I know that if I have the same base and the same term, it's going to equal 1, I'm going to manipulate that to use this. So instead of using the x, what if I use log base 2 of 2x? And what I do on one side, if I do it on the other, then it doesn't change anything. I'm taking the log base 2 of both sides. But since I'm doing it to both sides, it doesn't actually change my problem at all. So I'm going to apply my property here and bring my exponent out to the front. So I get x log base 2 of 2 is equal to, and nothing happened on this side, so I'm just going to keep it like that. All right, well, if I apply this rule, this part here is just equal to 1. So I can leave this as x is equal to log base 2 of 7. Now you can go into your calculator and plug this in, but I don't want to get into calculators yet, so I'm just going to leave my answer like this. The x is by itself, therefore it doesn't matter how ugly it looks on the other side, because the x is already by itself, and that's all I wanted. So you go ahead and solve this next one on your own. Go ahead and pause here so that you can solve that, and then when you're ready, I'll have the key for you. All right, so you should have something like this. I used log base 3 so that I can get rid of that base 3 here. And when I did that, the x became my coefficient. This equals just 1. So I was left with just the x by itself. And in this part, you could simplify it if you wanted to use the calculator for that, but because I'm going to assume you only have your phone calculator, I don't want to do that on the phone. I'm just going to leave it like this. And on your test, you can leave it like that. That's one of the options. Okay, so for this next part, these are similar, but you can see they're a little bit more complicated. So I'm going to start off the same way. I'm going to say, again, the 7 is going to tell me what I want my base to my log to be. So log 7, and I'm going to color code these just because it's going to get a little bit tricky here. So log 7 to both sides, I'm going to bring my 7, 9x, and then my 15. So I know I want that 9x to be a coefficient. Log base 7 is 7, which is exactly what I want because I know that that's going to cancel out to 1. And then log base 7 of 15. So this is going to go away to 1. So I get 9x is equal to log base 7 of 15. Now I want the x by itself, so I have to get rid of my 9. And what I do on one side, I have to do on the other. So x is equal to log base 7, 15 over 9. And again, it doesn't matter how ugly this gets. This is a 7 here. It doesn't matter how ugly it gets because all you want is the x by itself. So the other side doesn't even matter as long as the x is by itself. So go ahead and try this next one. That's going to be like our challenge question. Pause here and answer that one. Okay, and here is this last one. So you see that this one is a little bit more complicated. This one was just the ones we started off with was just the x, and then I added a coefficient to that. But then this one, not only did it have an x and a coefficient, but then I also added a term that you were subtracting at the end. So we're going to take each one of these one step at a time. When you pick your log, you can pick anything that you want at all. As long as you do it to both sides, it's not really affecting anything. So why not manipulate it so that it completely eliminates a term in itself? And that's what I did. That's why I chose the 4 here, and that's why I chose the 7 here. You want the 7 and that 4 to cancel out by this property up here. Okay, so log 4 on both sides, that's what I did. Now, I turned my exponent into my coefficient because of log properties. I can do that. This canceled out to a 1. So I brought this down. And then this just got brought down again. Nothing happened to that part. Now I want the x by itself, so I'm going to add 2 to both sides. Now I can't combine it to the 7 because that's inside of your log. So it just gets added to the end. And then I want the x by itself, so again I'm going to divide both sides by the 3. And I get this. An ugly looking thing that doesn't really matter. This is a 3. Because all you care about is that the x is by itself. So I'm going to go ahead and end this video here because it's getting pretty long. And we'll have one more shorter video on change of base formula. And then that's it. I'll do change of base and I will recap this, and that'll kind of be your your chapter review video. Okay? Be good, be great, be beautiful, and good luck.